This is lecture 3.2. It's titled Are All Atoms Equal? It says great minds discuss ideas, average minds discuss events, and small minds discuss people. So the learning goals for this are students will understand the process by which an ion will form. You will be able to differentiate between an ion, an atom, and an isotope, and that you'll be able to calculate the average atomic mass. So what you already know, you know that atoms are made of protons, neutrons, and electrons from the previous lecture. You also know that experimental evidence led to the development of the current atomic model, or the one that we're going to use in this class, which is the Bohr model of the atom. So in the lab, you learn that beings like atoms can vary in mass. The average atomic mass is determined by finding the mass of a large sample of atoms and then kind of dividing it out. It will account for the discrepancies in mass. All right, so first we have ions. Now, ions are electrons can be added or removed from an atom. Now, we've already talked about this real briefly, and the fact that an atom you can have an atom that has a different number of protons than it does electrons. Whenever that's the case, it's called an ion. Now, what we define them as is an anion. An anion is one in which there are more electrons than there are protons, and cations are one in which there are more protons than there are electrons. Anions tend to be on the right side of the periodic table. Cations tend to be on the left side of the periodic table. So for ionic notation, we've already discussed this briefly. Whenever we write something in ionic notation, what it allows us to do is specify the number of protons and electrons that are present in an atom. You will use ionic notation you'll use it quite a lot. So the first thing you need to do is identify the number of protons. For example, if you were to look at this particular example, you have 1, 2, 3, 4, 5, 6 protons. Once I've identified it as 6 protons, I can write the chemical symbol for this particular element, and that would be carbon. Okay, the next thing that I would do is I would determine the number if the object is a cation or anion by figuring out what the surplus or deficit of electrons are. So there are 4 total electrons. So in order to figure out if there's a deficit or a surplus, I would say the number of protons minus the number of electrons, and that is a positive number, which is 2. So I would express this as 2 plus. That is how you write the ionic notation for this particular atom. Now notice, it's not like nuclear symbol notation where you have the isotopes or the number of protons there. In ionic symbol notation, all it is the element and then the difference between the protons and the electrons. So when we talk about ionization energy, whenever something is an ion, what it means is that generally speaking, when we talk about ionization energy, is that the energy required to remove electrons. Now, the energy required to remove the electrons depends on a couple of factors, and we'll go into this in more detail in a later lecture. But the number of positive charges, the more positive charges there are, the more difficult it is to remove a negative electron because opposites attract. The stronger the positive charge, the stronger it's going to pull a negative charge. Also, the number of negative charges. If there's a whole bunch of negative charges in between, like electrons that are full, that's actually going to make it easier to remove an electron. And finally, the distance between them two. The shorter the distance between the proton and the electron, the more difficult it is to remove the electron. Ionic radii. So the ionic radii, most of the times what we do is we compare it to the element that it most closely emulates. So if you were to look at this, you would say a lithium ion is very close to the same size as a helium atom because both of them have 2 electrons in their orbitals, and they have the same number of orbitals. So they have one orbital, each one has 2 electrons. Now there is a slight difference because of the fact that this has 3 protons and this only has 2, but we'll talk about that a little bit later. So the first thing we want to do is we want to be able to write the ionic notation for an atom with the following characteristics. Now the first thing that you should realize is when we're talking about ionic notation, this does not matter whatsoever. So with the first thing we do is we say I've got 4 protons. I need to identify that particular element, which is beryllium, because it's the atomic number of 4. The next thing I do is I always do protons minus electrons. In this case, it's a positive number, so I would put Be2 plus, and that would be my answer. Next, it says the attraction and repulsion between protons and electrons is responsible for the atomic ionic ionization energy and electronegativity. Explain how increasing the period of an electron decreases the ionization energy using the formula below. This is a formula that you will use quite a lot in physics. It's actually called Coulomb's law. And if you look at it, it explains that the distance between the charges, charge and charge, it says increasing the period of an electron. Remember, when you increase the period of an electron, you're adding another layer of electrons. In other words, you're vastly increasing the distance. If you increase the distance, remember this distance is on the bottom, so you're dividing by a larger number. Not only that, but it's a squared term. So if you increase the distance by a factor of 2, you end up decreasing the force by a factor of 4. Mastery A3, it says, under what circumstances might helium have a greater electronegativity than fluorine? Fluorine actually has the greatest electronegativity. It wants an electron more so than anything else. And I want to say, well, how can I make helium want an electron more than anything else? Now, if you were to look at Coulomb's law, we have charge, charge, and distance squared. So the only advantage that helium has over fluorine is the fact that the electrons are much, much closer to one another. In other words, if I have an electron right here, it can be attracted to the positive nucleus because the distance is so much smaller. But helium is a noble gas and does not want an electron. So what we have to do is we have to make helium somehow want an electron. And we do that by ionizing helium. When we ionize helium, we're taking an electron away. So now helium becomes positive charge and one electron. At that point, helium has an electron deficit and would greatly want another electron. That's the only way to make helium more electronegative than fluorine. Next, we have, are all atoms equal? It says an extension of Thomson's experiment. So we talked about Thomson's experiment last time and how he discovered the electron by firing it between two charged plates. Well, an extension of that experiment actually led to two different lines of neon. If you look, there's a line for neon and there's another line for neon. Now that was really interesting to scientists because the only thing that this could possibly imply was the fact that there was neon with different mass. And so this was the experimental evidence that we have isotopes. Isotopes are atoms that have the same number of protons, the same number of electrons, and because of this, they have the same reactivity. You can't tell the difference of them chemically, what they bond with, but they do have a different number of neutrons, and therefore they have a different amount of mass. A lot of times you will see them referred to helium-3 or helium-4. This one right here would be helium-3 because it has an atomic mass of 3, or it has 3 things in the nucleus. This one right here would be helium-4 because it has 4 things that are in the nucleus. If you notice, this atomic mass term right here does not include the number of electrons because the electrons are so small. So we talked about nuclear symbol notation before, where you identify the number of protons, you had chemical symbol, the atomic number, and the atomic mass, but you should be familiar with those. We also are going to now formally put in adding in charge. You can also put in the ionic notation right there that indicates the number of protons, or the difference between protons and electrons. So in this particular case, I would say that this atom has 2 protons, 1 neutron, and 3 electrons based on this nuclear symbol notation. Okay, because this is the protons, this is protons plus neutrons, so you subtract to get that. This right here indicates that there is 1 more electron than there is proton. Okay, so likewise for this, I would say that this has 2 protons. At this point, I would say it has 2 neutrons because the difference between those is 2. And I would also say that this thing has 1 more proton than it does electron, so therefore it must have 1 electron. So for atomic mass, if all the atoms of hydrogen or all the atoms of helium are different, how can you come up with the atomic mass of hydrogen? And the answer is you actually come up with what's called the average atomic mass. Most elements consist of one major isotope. For example, if you look at hydrogen, 99.98% of all the hydrogen is 1.007825032. But you have 0.0115 is this right here, which is often called deuterium. And an even smaller amount is called tritium. Now, tritium is interesting because they use it to make nuclear bombs, but there's such an incredibly small amount of it. So the question is well, what is the the average mass, or what is the mass of hydrogen if you have these hydrogens that have different masses. And you go through a procedure in which you calculate the average atomic mass. Now, it's really important that you just say, oh, there's three different isotopes, add them up and divide by 3. You can't do that. This is very similar to how your grades are calculated. Some grades are calculated at the 70%. 70% of your grade, major grades, quizzes, tests, those sorts of things. Some of them are evaluated at 30%. You can't just take your number of daily grades and your test grades and add them up and divide by the number of grades, because they're weighted differently. And it's the same thing when we talk about the average atomic mass. They're weighted differently. So the first thing that you need to do is you need to change the percent to a decimal. And that's what we did here. You take these percentages, you divide them by 100, and what you end up with is decimals. Once you have these decimals, now you create what's called a weighted average. You multiply the atomic mass by the decimal, and you get your contribution to the total mass. Now, the final step that you need to do is you take these contributions of the total mass and you add them together. When you add them together, you get this total number right here, which is 1.00787. Next, we have developing B1. It says, write the nuclear symbol notation for a carbon atom containing 8 neutrons. So the fact that it's a carbon atom lets me know that it's going to be a C. I also know that there's going to be a 6 right there, because that's the average, because that's the number of protons. Okay? The fact that it has 8 neutrons lets me know that this is going to be 14, because this number right here is the number of protons plus the number of neutrons. And finally, there is no reference to the number of electrons here, so I'm going to assume that protons equals electrons, so that is the nuclear symbol notation. Next, it says, using the data below, determine the average atomic mass for iron. Now, I'm going to set this one up for you, but I want you to finish it on your own. What you do, remember, is you always convert these percentages to a decimal. So you move it over 2. That's the same thing as dividing by 100. So it's 0.0584. It's 0.91754. It's 0.02119 and 0.00282. Now you multiply these numbers across. So 53.9396127 times this equals, times this equals, times this equals, and so on and so on and so on. Once you get these numbers, you have to add them together. Now, the one thing that I will caution you about is significant figures. If you notice, this has 3 significant figures. When I multiply it by this number with whatever it is, 10 significant figures, the answer can only have 3 significant figures. Okay, be very careful when you do these calculations, because you need to make sure that you follow the rules for significant figures. And then you should be able to calculate the average atomic mass from there. The last one says the average atomic mass of chlorine is 35.45 when accounting for the 2 naturally occurring isotopes. It says the isotopes are shown below. What is the percent abundance of each? Now, this one can be kind of difficult for you to do, so let's look at it real quick. You don't know the percent abundances, so you don't know this decimal. But you do know the total. So whenever you multiply those things together, you know that that's 35.45. Now, a lot of times when we don't know a number, what we do is we represent it by an x, and that's what I'm going to do here. I'm going to represent this as an x. Now, the advantage of this is, what is the total percentage of these 2 isotopes? It says these are the only 2 naturally occurring isotopes. So together, these things have to add up to 100%, or 1, whenever you look at it in a decimal form. So I can reference this as 1 minus x. So now I can multiply it across. I can say something like 34.9688572 plus 1 minus x times 36.96590.262. When you take these things and you add them together and you multiply them out, they have to equal 35.45. Well, now if you look at it, I only have one variable that I don't know. I only don't know x. Now I have to be careful in distributing and solving and rearranging, but when I do that, I'll actually solve for a decimal that's x. one way to kind of check your answer is that X has to be less than 1 because you can't have more than 100% of it be a certain value. So I'll leave that for you to solve. The next one says a particular mass spectrometer ionizes a sample to a stable form and then separates the components with different mass to charges. Would a mass spectrometer be capable of separating the two substances below? Now, this one is really tricky because this element is in group 2. This element is in group 1. So the way they ionize is this becomes a charge of +1, this becomes a charge of +2. So now the question is can they be separated based on different mass to charge ratios? If you're looking at a mass to charge ratio, you're looking at the top two numbers. Okay, so if I were to take the mass and divide it by the charge, I would get 20. And if I were to take the mass and divide it by the charge, I would get 20. So this particular mass spectrometer would be incapable of separating calcium from sodium.